Lesson 13.3, Riemann and trapezoidal sums from equations. So now we have no table, no graph. Let f be the function divided by f of x equals 6 divided by x. If three subintervals of equal length are used, what is the value of the left Riemann sum approximation for the antiderivative of 6 over x from 2 to 6.5, round to the nearest thousandth if necessary? So first what I would want to understand is that the subintervals this time are of equal length. So we need to find the distance we're covering for our x value. So you take 6.5 minus 2, and then it says they want us to have three subintervals. So 6.5 minus 2 would be 4.5 divided by 3. And that is 1.5. So let me make a table real quick. And we know we're starting at an x value of 2. And then I know I'm counting by 1.5. So 2 then would be 3.5. And then I know plus 1.5 is 5. And then 6.5. And so that would give me my 1, 2, 3 intervals. Okay, and so then I want to just think, instead of actually figuring out a number here, let's just say at x is 2, our y value is going to be whatever f of 2 is, right? We're plugging in 2 for x, we're going to get out a y. Here it would be f of 3.5, here it would be f of 5, and f of 6.5. That'll be a little bit easier for my table. Okay, so to find the area, then I'm going to use the left-handed sides. So I'll have, using this left, this left, this left. We're not going to be using this one. So I'll figure out, okay, every time I have a width of 1.5 times, it'll be f of 2, plus another width of 1.5, f of 3.5. Plus, one more time, I'll have the width of 1.5 times f of 5. Okay, so then our equation every time is 6 divided by x. So if I plug in 2, 6 divided by 2 would make y be 3. So I'd take 1.5 times 3 plus 6 divided by 3.5 would be that, yuck, times 1.5 would be 2.571. As long as we round to the nearest thousandth on all these, we should be good. And then plus, I'm going to plug in 5 here, so that'd be 6/5 times 1.5. I'm going to get 1.8. And then I want to add all those up. So 1.5 times 3 plus 2.571 plus 1.8. And I'm getting 8.871 for the total area. All right, number 2. F is a new function. It's x to the 4th power. 5 subintervals of equal length are used. 5 subintervals of equal length. What is the value of the midpoint Riemann sum? We're going from 0 to 2. Okay, let's make a table again. Start at 0. We need to figure out how wide our subinterval rectangles are going to be. So 2 minus 0 divided by our 5 subintervals. We keep getting fractions. That'll be 2/5. 2/5 is the same thing as 4/10. I'm just doing some mental math here. 4/10 is literally the decimal 0.4. So that's what my width's going to be every time. So I'm going to go from 0, I'm going to have 0.4, plus a 0.4 would be 0.8, plus a 0.4 would be 1.2, plus a 0.4 would be 1.6, plus a 0.4 would be 2. And we know these are all f of x. F of 0.4, f of 0.8, f of 1.2, f of 1.6, and f of 2. Okay, we're doing midpoint. So now the problem is I need to know what this middle is. And so I probably should have added that on my table, but I didn't. There should be 1, 2, 3, 4, 5 here. So the other thing you can do that's kind of nice is since these are all equal widths, you can actually have 0.4 on the outside and multiply that at the end after adding all your heights. And so we know that right here halfway between 0 and 0.4 be 0.2. So we need actually f of 0.2. This would be 0.6. We need f of 0.6. This would be 1. We need f of 1. And then we would need 1.4. So we're actually adding 0.4s to these, right? And then that would be 1.8. Okay, so then on here, try to save room, I need f of 0.2. So I'm going to have 0.2 to the 4th power is 0.0016 plus I need 0.6 to the 4th power. It's 0.1296 plus I need f of 1, easy enough, 1 to the 4th is 1. I need 1.4 to the 4th power, 3.8416, and I need f of 1.8, so 1.8 to the 4th power. 10.4976. Okay, I'm going to add all those up, and then I'm going to take them times 0.4. And I got the total area to be 6.188 rounded to the nearest thousandth. All right, number 3, new function, 6 to the x power. If 4 subintervals of equal length are used, what is the value of the trapezoidal sum from 0 to 2 rounded to the nearest thousandth? Okay, so make a table if that helps. Starting with 0, so 2 minus 0, that's 2, and then divided by 4 subintervals. So that means they're each a half. Okay, so I'd go 0.5, 1, 1.5, 2. So that's f of 0, f of 0.5, f of 1, f of 1.5, and f of 2. Okay, remember trapezoids, you can do 1/2 times the whole thing, or if you'd rather have the bases. The good thing on this is you could have your 1/2, because that's always in the area of a trapezoid, and then your heights, since these are equal subintervals, your height is always going to be a half. So you could have 1/2 times 1/2, and then all we would have to do is add up all the bases. So do you get what I'm saying? Instead of having where in your formula we're going ahead and doing our 1/2 times our height's 1/2, and then all we have to do is add up all the bases. And so our first interval will have f of 0 and f of 0.5. So 6 to the 0 power is actually 1, plus 6 to the 1/2 power is that. I'm going to say 2.449. Okay, then my next trapezoid will have these two. So what they're going to have is actually 2 of these. The first one's only used once, but then these two will use this and this. So I'm actually going to take this times 2. And I'll take care of that. Then I'll have f of 1, 6 to the 1st power is 6. But then for my next interval, I'll have to use that again. So instead of adding 6, I'll just say times 2 plus 6 to the 1.5 power, 14.697. And then plus, times 2. And then plus, I'm only going to need 1 of these as well. So the outsides don't get used twice. So f of 2, that'd be 6 squared, which is 36. Okay, let's figure out what that is. So total I get for all this inside is 83.292, and then I did my 1/2 times 1/2, which is a 4th, which is 0.25. So I'm going to take this times 0.25, and I should get 20.823 as my area. But again, you can make this formula as lengthy as you want. If you didn't like doing this, do each trapezoid. Have each this plus this over 2 times the height of 0.5. You can do each one individual if you'd like.